If you've done any 3D printing, you know that the printing process produces a lot of waste. Unfortunately, there isn't a viable method to recycle all these failed prints and support material, which means that most of it ends up in a landfill. The goal of this project is to solve this problem by turning old prints back into usable filament. For our design to work effectively, we need to be able to extrude a long continuous strand of circular filament. Because of this objective, we have three main design constraints. The first is a target diameter of 1.75 millimeters, which is the industry standard for 3D printer filament. Second, we want to be able to recycle the most common 3D printing material, PLA, which means that our system must withstand temperatures of at least 220 degrees Celsius. Finally, we wanted to achieve a reasonable extrusion rate, setting our target at 0.5 kilogram per hour.
To meet these design goals, our team came up with several possible solutions, but eventually landed on a vertically oriented heated pipe design. The system can take PLA stock pellets, old shredded prints, or a mixture of both. The stock is fed into a hopper and driven through the heated pipe by a slowly rotating auger. Once it is heated up enough, the PLA is pushed out through a circular nozzle and quickly cooled back to room temperature. The new filament is then spooled using a laser gate system and a low RPM motor.
When designing the system, there were a few major decisions made. First, we conducted a heat transfer analysis to decide how much power our heating elements needed to output, and this helped us choose a pipe material and dimensions. Second, we did a fluid analysis on the viscous PLA to determine the torque requirements of the main motor. As we went along, we ensured that our components could withstand the temperatures and currents required. When comparing our results to our design constraints, we found that our filament was slightly smaller than our 1.75 millimeter target, which could easily be fixed by changing the diameter of our nozzle. The diameter also varies much more than in the stock filament, which claims to be within 0.03 millimeters of the target diameter. Our system withstood the required temperatures and was able to extrude at a rate of about 1 to 2 feet per minute. This is about 6 times slower than our target extrusion rate. When comparing the physical properties between the stock filament and our filament, they are fairly similar. Some of our filament was a bit more brittle than stock, but comparing them side to side, as you can see here, our final product, we can see it's fairly bendable to the same level as the stock filament.
If we could start this project over, we would have done a few things differently. First, we would have opted for a thinner pipe to decrease the preheating time. It took about 20 minutes for our pipe to get to temperature, which is not something that we thought about in our initial design stages. Once it was up to temperature, we had a dangerous hot pipe that could easily injure the user. To fix this, we would design an insulated enclosure that would prevent accidental contact that would potentially lead to burns. Next, we would have used insulated thermocouples rather than trying to insulate them using capped-on tape to prevent them from shorting on the pipe. Finally, we learned that we should have accounted for failure modes much sooner than we did. We could have saved a lot of time by putting in protections against component failures before they happened rather than after.